Welcome to my talk about time-dependent tourist tour planning with adjustable profits by Tim Witzel and myself. So when planning a tourist tour, we need to consider several constraints like opening hours, the public transport timetable, and we need to consider where to leave and enter an attraction. We need to consider the walking times inside and outside of attractions, and we want to avoid redundancy when planning multiple tours. And choosing the visit durations is not easy because we don't want to visit the POI for too long or for too short. And of course, visits are depending on interest because, for example, a family would like to go to a playground more than an elderly person. When modeling this problem, we consider static inputs, the user input, and we produce an output. So as static input, we have the public transport timetable. We need to know about the pedestrian routing network, which we extract from OpenStreetMap. And for each POI, we need to know the opening hours, the categories, the coordinates of entries and exits, as well as the walking times between entries and exits, and the profit function, which tells us how long to stay. So this is time dependent. As user input, we take the start coordinates, like the position of the hotel or the arrival public transport station, and the destination coordinates, which can be the same as the start coordinates but don't need to be. And the user also provides the start time of the tour as well as the maximum tour duration. And the user needs to provide the weighting of POI categories. So as an output, the algorithm produces in the order of the POIs with the corresponding visit times and the used public transport trips, including the stop where to enter and where to exit the trip. So for modeling the profit function, we take into account that there's some time t-min visit, and staying shorter than t-min visit does not make sense, but also staying longer than t-max visit does not make sense. And in between we have a linear function of time, so staying longer increases the profit linearly within the range between t-min visit and t-max visit. So for each POI we have the profit per time gained in this interval. So this looks like this function. So until t-min visit we have no profit, and there's no further profit after t-max visit, and in between we have a linear function. And we can also model events with this function, like a theater visit, which has a fixed time, and then we set the max visit after this fixed time, and before this fixed time we have zero profit. So when modeling this as a mixed integer linear problem, we obviously have the objective function, which is the sum of all PIs over all tours visited. And we need to consider constraints. Unfortunately, we don't have time to discuss this in detail, but of course we need to make sure that the first location is left exactly once and the destination location is arrived at exactly once. And for each POI we have at most one visit, and we leave the POI exactly the same time as we enter it. We need to respect the maximum tour length and the minimum walking time between locations, and we need to ensure the visit times and travel times. And this is how we model the piecewise linear profit function. And of course the opening times need to be respected as well. So in our pre-processing, we choose a granularity and for this granularity we do a routing request from each point in time, from each POI to each other POI. So this gives us the shortest path, and from these shortest path we can construct an event activity network. So we have here, for example, POA A, and if we leave at 9:30, we arrive at POA B at 9:40, and by doing this for every time slot, we have all options to travel between POIs. Gets a bit more complicated if we have multiple locations per POI. So we have some edges between entering and leaving the POI location. We have edges to switch between POI locations, and we have edges to switch between POIs. So on this graph we can execute a greedy algorithm. So we build a tour from start to end by adding one activity at a time, and the greedy algorithm chooses this next activity based on a simple metric, which is profit per time, and we weight the travel time against the visit time, and we keep a set of already visited POIs to prevent revisiting POIs. And additionally, we need a dead-end protection because there are POIs from where it's not possible to reach the destination within the maximum tour length. So we need either to have a look ahead, a backtracing, or we prune the graph to remove those nodes where reaching the destination is not possible. So in our case, we chose to have a look ahead. And then we have an advanced greedy algorithm, which basically is the same as the basic greedy, but we track multiple solutions and make multiple expansions in each step. We introduce a cutoff threshold based on the profit per time, and if the solution is worse than the profit per time times the cutoff of the best solution, we remove these bad solutions from the list of kept solutions. Since in related work the iterated local search approaches scored very well, we also implemented an iterated local search. So this is our basic version of the iterated local search, where we combine the local search and the perturbed step. Our neighborhood in the local search step is defined as all solutions which can be produced by integrating a visit into the tour while still keeping the solution feasible. And in the perturb step, we remove increasing numbers of POIs to escape the local optimum. In the advanced iterated local search, the perturb step also is enabled to shorten the visit times, and the local search step is enabled to lengthen the visit times. So in this advanced version we can also play around with the visit times. In our evaluation we gathered all POIs of Berlin we could find and got the opening times as well as the locations. So this is a map of them you can see here. We defined tour requests of different length and different tour counts. We measured the preprocessing performance, and preprocessing for the Berlin case takes around 50 minutes, which is reasonable, I think. And we analyzed for different granularities, and we discovered that the graph size roughly scales with the granularity in a linear manner. So we evaluated the algorithms on this graph, and the basic greedy algorithm is very simple, so it takes only about 2 to 4 milliseconds. And the advanced greedy obviously scales with the number of solutions we want to track in parallel. So this is from 1 second for 100 solutions to 500 seconds for 100,000 solutions. So the first two versions are within a reasonable time a user would wait for this, but I think for these 50 seconds and 500 seconds, this is not something we want to deploy and practice. So for the basic iterated local search, this takes about 1.5 seconds, and the advanced iterated local search takes around 5 seconds. We compared the results with the mixed integer linear program, which we feed it into Gurobi, and we halted Gurobi after 10 hours. So there are some cases where Gurobi did not provide the optimal solution. At least the iterated local search and greedy algorithms could improve upon the solution of the Gurobi solver, but in most cases the Gurobi solver provided a higher quality than the greedy and iterated local search approaches. So we see here the blue dots are the best solution of all approaches, and the red dots are those approaches that provide the solution within 10 seconds or less. So the red dots would be the reasonable version to use if the user wants to wait for the solution online. So this was it. Thank you for your attention.